When an object is heated, heat energy is transferred to that object's thermal energy store, in the form of kinetic energy for the object's particles, resulting in a rise in the object's temperature. Heat may be transferred in one of three ways, depending on the medium through which it is transferred. Thermal energy transmission occurs all the time, from the hot plate that cooks your meal to the fireplace that maintains a pleasant temperature. But in order for thermal energy to transfer from one place to another, there must be a temperature difference. In the next few minutes, we will go through conduction, convection, and radiation, which are the three methods by which thermal energy is transported. Heat transfers through solids by conduction. Heat transfers through liquids mostly by convection. Heat transfers through empty space by radiation. Let us start by conduction. Conduction transfers heat energy by physical contact, and thermal conductivity is a measure of how quickly heat energy can be transmitted from a warmer zone through the material to a cooler zone. Here is an experiment to show one way to compare thermal conductivity of different material. Here we have four rods of the same size and different materials. Each has a blob of wax at one end, and they are all heated equally at the other end. The best conductor is the metal on which the wax melts first. The results of this experiment demonstrate that the wax on the copper rod melted first. Then the wax on the aluminum, the brass, and finally, the iron. In fact, conduction is the primary method of thermal energy transfer in solids. Although metals are typically much better conductors than nonmetals, both metals and nonmetals can conduct heat. This is actually a result of the different ways that heat transfers through metals and nonmetals. Here is an explanation of the heat transfer mechanism in nonmetals and metallic materials, using the particle model of matter. In fact, heat is transferred through nonmetals only by atomic vibrations. In that mechanism, heating one end of the nonmetallic matter makes its molecules move faster and vibrate more, which causes them to bump into nearby atoms and give some of their energy to them. This way of sharing heat will slowly move energy from the end that is hot to the end that is cold. In metallic materials, heat is transferred by more than just the atomic vibration mechanism. Free electron collision mechanisms also play a role. These mechanisms are more efficient at moving heat energy, because the electron's small size allows them to travel further. Before we go on to the next method by which heat energy is transferred, let's look at a common example of how heat conduction works on a cold day. Even though both are at room temperature, the bathroom floor will seem cooler than the bathroom carpet. Because the stone floor conducts heat better than the bathroom carpet, more heat from your foot will rapidly pass to the floor, making it seem colder. The foot on the carpet, on the other hand, will not lose heat energy as quickly, making it seem warmer. In truth, what you feel is the temperature of your foot, not the temperature of the object you touch.
Excuse me, does any heat transfer happen via the process of conduction in liquids and gases?
Okay, the short answer is that yes, thermal conduction does happen in both liquids and gases. However, both liquids and gases are very poor at transferring thermal energy by conduction. Having said that, I'd want to give a more detailed version of the answer to prevent any misunderstanding. Conduction is one of three methods for transferring heat energy. It is the transmission of heat energy by collisions between neighboring atoms, molecules or electrons, and, as we all know, particle separation differs across the three states of matter, with gas having the most separation and solid having the lowest. Therefore, heat transmission in solids by conduction will be the highest, and heat transfer in gas by conduction will be the lowest. At the end of our discussion of thermal conductivity, please keep in mind that, since the concentration of free electrons in a material increases its heat conductivity, there is a broad range of thermal conductivity, ranging from good conductors to good insulators. Convection is the process by which heat moves from a location that is hotter to a location that is cooler, because of the movement of the heated material. In fact, this process is also known as the convection current. In this image, for example, heat is being transferred from the fire to the hand above it by the rising current of hot air caused by convection. In this situation, the heated material itself, which in this case is the air, is moving and transferring the heat energy. On the other hand, if I place one end of the fireplace poker stick on the flame, the rest of the stick's material will then receive heat from the flame end through the conduction process, which is caused by the movement of free electrons and the vibration of atoms and molecules inside the stick without any movement of the stick material itself. Let us start an experiment to show the convection current in water. Because water is clear and colorless, we will be using crystals of potassium manganate to act as a purple dye to show up the movement of the water. Let's see what happens when we light the flame. Mainly by conduction, the flame heats the bottom layer of water in the flask. When the water is heated, the molecules will push apart, making the water less dense. Because of this, the water that is less dense rises and sends heat to the higher layers, while water that is cooler comes down and replaces it. The cooler water will then heat up, rise, and be replaced by less hot water at the top. And this cycle will keep going, as long as the system keeps getting heat energy. Before we end our discussion about the convection current, I want to make two more points. First, convection is the primary method for transferring heat energy through fluids, whether they are gases or liquids. Second, convection cannot happen in solids. Again, using the campfire as an example, we saw how convection and conduction transfer heat energy. But if you placed your hand away from the convection current and placed it on the site of the flame, you would still feel heat, which is due to thermal radiation, the third method of thermal energy transfer. In fact, thermal radiation is the electromagnetic radiation given off by an object as a result of its temperature. Let us state some facts about thermal radiation. All objects with a temperature above absolute zero emit thermal radiation. The hotter an object is, the more thermal radiation it gives off. At room temperature, most of the emission is in the infrared spectrum. However, if solid matter does not vaporize, it begins to glow in a visible red color at about 500 degrees Celsius, then yellow as the temperature increases, and finally white light. In fact, we will go over the electromagnetic wave and the electromagnetic spectrum in greater detail in Unit 3. But for now, remember that infrared and visible light are both parts of the electromagnetic spectrum. Thermal radiation is the only way in which heat can travel through a vacuum. In fact, it is the way in which heat reaches us from the sun through the vacuum of space. However, while thermal radiation is the only way for heat to travel through a vacuum, it can also penetrate through materials. For example, thermal radiation can travel through the air to reach a handsome distance from a flame. The only difference is that when it passes through a vacuum, it doesn't get weaker like it does when it passes through matter. This should explain why moving your hand away from the flame makes you feel less heat. In fact, as an application for the ability of thermal radiation to penetrate through objects, it's common practice for water pipe workers to use heat-sensitive cameras to inspect pipes behind walls before starting to work. Thermal radiation travels in straight lines and heats the object that absorbs it. The color of an object affects how good it is at emitting and absorbing thermal radiation.
I know this may seem foolish, but please bear with me while I try to understand this. As long as anything with a temperature above absolute zero continues to radiate thermal energy, why hasn't everything around us lost all of its thermal energy and cooled to absolute zero?
In fact, that is a very good question, and it will take us to our next topic, which is thermal equilibrium, which exists when two objects in thermal contact no longer affect each other's temperature. For example, if a carton of milk from the refrigerator is placed on the kitchen counter, the two objects are in thermal contact. After a few hours, their temperatures will be the same, which means that they have reached thermal equilibrium. Yes, it is true that when objects emit thermal radiation, their temperature will drop, but when the object absorbs thermal radiation, it will become hotter. Eventually, all objects will reach a point of constant temperature, where they absorb thermal radiation at the same rate as they emit it. At this point, the object will be in thermal equilibrium. We all know that differences in temperature change the rate at which an object radiates or emits thermal energy until it reaches a state of thermal equilibrium, where the rate of absorption equals the rate of emission. So, if I have two identical objects, one of which is hotter than the other, the hotter one will emit more thermal energy. However, if both objects are cooler than their surroundings, the cooler object will absorb more thermal energy. In this section, we'll look at how the surface color, surface texture, and surface area of an object affect the rate at which objects emit or absorb thermal energy, assuming the same temperature difference between the object and its surroundings. Before we get into the details of this section, I want you to keep in mind Kirchhoff's radiation law, which states, objects that are good emitters are also good absorbers. This table shows how the color and texture of a surface affect the rates of thermal energy absorption and emission. This table demonstrates that black surfaces are the best thermal energy absorbers and emitters, while white surfaces absorb and emit thermal energy poorly. Shiny textures are very poor, and even reflect radiation. Of course, it might be obvious that a larger surface area will result in more radiation and absorption. In fact, I felt this picture did an excellent job of displaying the effect of object color on thermal radiation output. While the entire surface of the cup is at the same temperature, the thermal image clearly differentiates the palm tree drawing from the rest of the cup surface. This is because the red color of the palm tree sketch emits more radiation per unit area than the white color of the rest of the cup's surface. The greenhouse effect is a natural process in which certain gases, such as carbon dioxide, water vapor, and methane, are known as greenhouse gases because they trap heat in the atmosphere, much like the glass walls of a greenhouse trap heat inside, causing the planet's temperature to rise and helping to keep the Earth warm enough to support life. In fact, if the Earth had no atmosphere, its surface would actually be emitting all of the sun's radiation into space, causing the temperature to drop to about -18 degrees centigrade at night, the same as the moon's surface. Actually, the majority of the heat on Earth comes from the sun as thermal radiation in the form of electromagnetic waves, mostly in the infrared, visible light, and ultraviolet ray spectrums. When the sun's electromagnetic radiation reaches the Earth's atmosphere, some of it is reflected back, and some is absorbed. The ozone layer blocks most of the harmful effects of ultraviolet radiation by absorbing the majority of the ultraviolet spectrum. As the electromagnetic radiation that was not absorbed by the atmosphere, mostly visible light and high-frequency infrared radiation, reaches the Earth's surface and is absorbed, the planet's internal energy rises, and the surface becomes hotter. At the same time, the Earth sends out its own thermal radiation, which has a slightly longer wavelength than the thermal radiation it gets from the sun, because the Earth's surface is much cooler than the sun's. The greenhouse gases, such as carbon dioxide, water vapor, and methane, absorb and emit infrared radiation in all directions, some out into space and some back towards Earth, which is then reabsorbed. That is what keeps our planet at an average temperature of about 15 degrees Celsius. In this section, we'll look at the connection between human activity and greenhouse gases, as well as their role in the global warming problem. As we now know, the primary greenhouse gases in Earth's atmosphere are water vapor, H2O, carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, and chlorofluorocarbons, are what keep the Earth warm enough to support life. In fact, without greenhouse gases, the average temperature of the Earth's surface would be about -18 degrees centigrade, rather than the present average of 15 degrees centigrade. By allowing the sun's light and heat in, but keeping part of the heat from leaving, like the greenhouse's glass wall. Increasing the greenhouse gases in the atmosphere due to human activity will increase the trapped heat, which will lead to what we now know as global warming. In fact, since the beginning of the Industrial Revolution, about 1750, Humans have raised the concentration of carbon dioxide in the atmosphere by more than 50%. Actually, the main source of carbon dioxide emissions is the use of fossil fuels for energy, transportation, and industrial processes. Deforestation, agriculture, and livestock farming are other major contributors to methane emissions. Nitrous oxide emissions are mostly caused by industrial activities and the use of fertilizers. There are actions that can be taken to reduce greenhouse gas emissions. These include increasing the use of renewable energy sources, such as solar and wind power, improving energy efficiency, planting trees and vegetation, and reducing deforestation. Now that we have finished going over the theoretical information for that unit, in the next part of this unit, we will go through some experiments that are included in both the core and the supplement of the syllabus. In the part after that, we will go over some past paper problems that are related to the information that we have studied in this unit.
See you soon.
Goodbye.